So this is a little bit unusual for us. We will have two main presentations, and we'll also hear about an upcoming project. So we have a third short presentation as well. How this is going to go is we will hear for 15 minutes from Jonas Nøland, who's a professor of energy machines and here at NTNU. I think that wasn't the exact title, but you can say it if you'd like. About his research on the role of nuclear in energy systems. Jonas has done some work recently published in the journal Scientific Reports, for example, where he takes kind of an empirical approach to thinking about the different technological characteristics and what that means. Then we'll hear about an upcoming project about nuclear from Martin Hjelmeland. And sorry if I butchered that. And finally, we'll hear for 15 minutes from Goran Durakovic, who is a PhD candidate. And he's done some optimization work considering the energy system and what role nuclear plays there. Since this is a bit of an unusual event, I have a few ground rules that I want to mention. So first of all, this is a topic that we're all generally very interested in. However, this is an academic forum. So what we're interested here is epistemically why things that we think might be true are true. So in other words, what are the strengths and weaknesses of different methods that we use in science? So this is the focus here. The focus is also on you, the audience, to understand what each presenter has done in their research from that presenter. So I will say this only once. This is not a debate. This is for the presenters to present their own work. And we have discussed this and told each of them that as well. And with that, I will first introduce Jonas to come here and begin his presentation. At the end, we'll have time for Q&A and discussion. I ask you to hold your questions during the presentations, and we'll get a discussion at the end. So Jonas, please take it away. You have this here. And this microphone, I assume that people online are hearing you pretty well. If it's just down there. So yeah, please take it away. Okay.
Okay. Thank you so much for the opportunity to share some of my perspectives with you today. I have a dream of a fossil-free world. Today we see that growth in primary energy consumption is going faster than renewables, and I think that nuclear will have a role to defeat the oil industry. A little bit about me. I'm an associate professor at NTNU, senior member IEEE. I have a PhD in engineering physics from Uppsala University. I'm the chair of the IEEE Power and Energy Society of Norway. And I'm an editor of associate editor of several IEEE journals, focusing on energy conversion and transportation electrification in particular. The first point I want to make to you today is that nuclear power is nature's best friend. I will, of course, base it on some of my research, but before I do that, I will try to look at also the consensus, because I believe on this issue, the consensus is on my side, not the people who believe that nuclear is not nature's best friend. So what I will show to you is what the EU's science panel is saying. They're saying that modern nuclear power is the safest source on Earth. It has the lowest land use, the lowest material use, the lowest CO2 emissions. They say that nuclear waste can be easily handled. Basically, when you have used the fuel, after 600 years, it's as dangerous as lead. It means you need to eat it to be able to be harmful to you. Future generations will living or handled nuclear waste will basically get an extra radiation dose of 2 bananas every year. That is the worst case that the EU science panel is taking. So the downside of nuclear is very, very minor when it comes to the positive side. Therefore, I will never say that nuclear power is perfect, but it's more than good enough for me. It's the energy source that I likes the least. That's the reason why I like it. The EU's science panel also say that nuclear power, because of this lifetime, because of very, very low amount of waste, that it can be handled, that it's not harmful, and so on, that it is as sustainable or more sustainable than alternatives. And if we want to have an energy-rich world in the future, and we want to defeat the oil industry, we still want to preserve nature, we need to reconsider our thinking. After the EU panel was coming up with their conclusions, their consensus, it got a lot of attack because the conclusions weren't so. A lot of people weren't so happy about the conclusion they had. So therefore, the UN came up with another report to back up the conclusions of the EU science panel, and they found that in this report that nuclear power, among all the energy sources that we can choose, it has the lowest impact on resource use. That means minerals and metals. It has the lowest negative impact on ecosystems. That means climate, nature, and environment. And the lowest impact on human health, including cancer. One example is that Germany's policy, it has been calculated that because of the dependency of nuclear power, or dependency on coal because of less nuclear power, it's estimated that 1,100 people need to die because of this policy change after 2012. So what about land use? What my research shows is that the land use, or the spatial extent of power generation, is rapidly increasing. We come from a world where we were depending on fossil fuels, natural gas, coal, and etc. Where the land use of electric power generation was very, very minor. We are rapidly electrifying the world. And today we have a spatial extent of our power generation that is 45 times larger than before the 2000s. If today's policies is of the International Energy Agency, the net zero there, which is the median scenario, which only assumes that the nuclear will increase twofold. There are other scenarios like the energy security scenario where nuclear will increase twofold, then the nature costs will be much lower. Actually, you could look at the future scenario where the county of Viken, half county of Viken, could be the area you use to give zero emission electricity and heat in 2050 in a carbon-free, emission-free world. The half the area of Viken Fylke would be enough to power the whole world with the massive electricity and a massive amount of heat that you need. So that gives you a perspective when you see there that what we need, with just twofold increase of nuclear, we need actually an area equal to the size of the European Union, or 1.5 times the size of India, to be able to get to net zero with just a decent increase in nuclear power. So net zero is not possible without nuclear power. That is there's no debate about that in the EIA or the UN and so on. The question is like, how much price are we willing to put on nature? And for some, if you talk about the biologists, some would say that the destroying of ecosystems is more detrimental to biodiversity than climate change. What the research I did found was that there's no debate that biomass is the worst energy source in this world. It's not only that it gives short-term emissions, it doesn't solve the air pollution problem. So, and also when you waste it on electricity with low efficiency, it's even a bigger waste. It's much better to use biomass for high value use. There's a lot of ideology coming to utilizing waste streams, where we kind of believe that there are more waste streams available than in reality. But still, there is an associated, even though it's a waste stream, it's an associated impact on spatial needs, and you don't solve the pollution problem. The most spatially dense technologies are hydropower, gas power, and nuclear power. Hydropower is maybe a little bit shocking to someone, because sometimes you see these studies done in the US where the land use of hydro is much bigger because of the landscape and so on. You have higher pole heights, you get much more energy density. So what I'm considering here, I'm not considering the catchment area, because like if you consider the catchment area, that would be the same as wind power, and the wind power would be even worse. Then you need to kind of consider all the area needed to heat up the air to make pressure differences and everything. So it would be very, very, I see often that you use catchment area for hydropower. That would be very, very legitimate, I think. And you would need to reconsider other sources as well. So it's therefore in this research, I tried to lay out like a methodology and I argue for every definition so that it's very, very clear what are my assumptions, and trying to back up the assumptions. So this is the final result of this research, where you quantify what is called the spatial energy density, the annual energy density in terawatt hours per square kilometer. And there you see that for every energy transition humans have explored in the past, we have never been through an energy transition without going from lower energy density to higher energy density. That was the way we got out of the nature crisis before the Industrial Revolution. And that's the reason why it's good reason to think that this energy transition will have a decent amount of nuclear power in the mix to make sure that the energy density will be high enough in order to have human prosperity, and also to solve other goals in the UN development goals, like fighting hunger, having decent economic growth in order to help humanity. The other part that is more in line with the project we have is the role of nuclear power in the energy system. And there we have a power adequacy crisis in Norway. We have kind of reached a place where Sweden was 20, 30 years ago, when they started putting nuclear at the bottom to be able to increase the value of hydropower. We see that in the future, in the worst case scenario, we don't have the amount of power when we need it the most. We will have really high price hikes, and the average price will skyrocket if we don't do anything on the long term. Norway has a lot of firm dispatchable power. We have 30 gigawatts. Sweden has 16. We have increased the installed power a lot the recent years. We haven't increased the firm dispatchable power. So in Sweden, they have 16 gigawatts of firm dispatchable hydropower. In Norway, we have 30 gigawatts. Now we have come to a place where we need to do the same as Sweden. We need to increase the value of hydropower. We need to get more flexibility out of the hydropower. And therefore, we need to have a source at the bottom with low marginal price that can be able to put in electricity to the grid most of the time. Hydropower is something you save. Nuclear power is abundant. That's not something you save. Nuclear power can be flexible, which Martin will share. There are systems that it needs to be flexible, but in our system it doesn't need, because you will actually free up firm dispatchable power by introducing baseload power with low marginal price. So yeah, this is a little sketch of how the price is set, and you have, of course, like price fluctuation because of changes in load, but you also have price fluctuation because of changes in supply. There you have distinguished between firm dispatchable renewables and intermittent variable renewables. What you can do to be able to show like why in the world today we see the only places where you have low stable electricity prices is where you have high amount of hydro or a combination of nuclear power and hydropower. These are the essential roles in combination with solar and wind to have stable electricity prices and low electricity prices. And the reason for that is that if you take supply fluctuations on the sources with the lowest marginal price and put it together with the consumption, so we say that the load is constituted of load, wind, and solar fluctuations. We see that nuclear power, the Nordic power system, nuclear power is the source at the bottom, stable with the lowest marginal price that is pushing down the electricity price the whole year, every hour. And that is assume that if you have a robust nuclear fleet where you are able to have one of the reactors on service every time. That is what Sweden had in the past before you had this power tax on nuclear, which was the anti-nuclear policy that was happening from 2017. So yeah,
Jonas, could you conclude in 1 minute?
Yeah,
Thanks.
Martin will say a little bit about all the services that nuclear provide, more than like electricity, where he will mention like reactor power, fast resource, black start capability, services, ancillary services that will be costly in the future, that you get for free with this type of generation. But you also get heat. So normally when you look at nuclear power, we look at the system here. We look at the electric utilization, but nuclear is much more than that. The most effective hydrogen production you can get from nuclear power by combining heat and electricity. You can use it for synthetic fuels, fertilizer. There's a food shortage, fertilizer shortage today because we burn up our natural gas instead of using it for high value. We already live in a hydrogen society, so we need to consider that and not burning it up, but actually use it for high value purposes. And we have also other purposes like water desalination and district heating and so on. So the final slide is just to say that hydrogen today is 92% is used locally. So that's the very, very good case for nuclear. That's not a good case for sources that cannot produce it locally. I've been researching electric aviation for a long time, so my passion is about nuclear-powered airport, where you don't need to put pressure on the grid. You don't need to put pressure on valuable firm dispatchable hydropower, and you can actually use these things for other purposes and make the energy transition much more easy. And at the same time, you can get much more hydrogen out of your electricity. So stable production, high uptime, and all the system cost, transfer cost, everything, considering everything, nuclear power will be by far the cheapest way to produce hydrogen. So that is also something we will look at in our project. So the final thing I will say, that's in Norwegian, en ekte naturverner spalter atomkjerner. Hadde vi spalta, så hadde vi spart Alta. Del atomet i 2, blir kvitt CO2, hold strømprisen i ro.
Thank you very much. We will now move to Martin Hjelmeland, and since we're running a little bit late, you'll do me a favor if you use a little bit less than the 5 minutes. But I know that I said 5 minutes originally.
No worries.
So I'm switching the presentation.
I guess this won't be the first, or this won't be the last time we can come here and present what we're working on. So
I hope so.
I'll try to be quick.
I hope that it's not the last time. So there you go.
Yeah, great. So as we said, just a few minutes about the research project we just started. So it is Jonas, me, and Magnus Koppås who started this internal nuclear energy role in a renewable energy system project, where we got some internal financings from NTNU. We have divided the project into 2 parts, where we're going to look at some power system studies. And as Jonas mentioned, in the end, there are some valuable properties by producing hydrogen from nuclear. So we're going to investigate that as well. So just to ask, isn't nuclear too expensive? Why are we bothering looking into this? There have been many chronicles and articles in the newspaper stating that is fact. However, if we look at some of the projects and see which one is the pointer. Oh, there it is. We can see some of the project that's been going on in the western part of the world. After they had this major build out in the 70s and 80s, they had a period of almost 30 years where they didn't build out anything. And then they tried to restart the nuclear build-outs project again. And by only building one plant here, special designs there, and it all ended up in extremely high cost. And, I think Olkiluoto 3 in Finland, it was 15 years or 12 years delayed. So there have been some major problems of these huge infrastructure projects in the western part of the world. But there are some countries in the world that are able to do this on time and on budget. So what are some of the reasons this is so? And if there is, the western part of the world can get their shit together and start producing on time and on price, maybe we can see a shift in nuclear build-outs in the West. Because adoptions normally don't happen like 1% a year, 2% a year. It happens suddenly. We have this tipping point where we can see the scale is shifting. So this is also a good point. Like some of the project that's been built in the West, they started building way before it was completed. And also they had to go back in the drawing board due to new regulations during building. So there's been some major obstacles for the Western projects that has delayed and made them very costly. So this is some of the reason we want to look more into and say that and do some analysis if we can get our shit together, how can we build out the nuclear in the West as well? So yeah, and this is also just an example of United Arab Emirates, where they recently, I think they're just finishing up this last unit, where they in 2008 decided to go for nuclear. In 2012 they started the first unit, and in 2015 they started the last unit. So build on time and on project. at a very reasonable price. And also in Poland, there is a lot of nuclear investments going on, where some of the bids that has come in to build out, I think it's 4 new nuclear plants. The 6, okay. So KEPCO, the South Korean company that built this project, build this project in the United Emirates, they have set a price just below $3,000 per kilowatt. And they also, in Poland, they want to build out 79 SMRs by the type of GE Hitachi BWRX 300. And they said at end of the kind, cost is between 2,000 and 3,000. So a little bit on how nuclear power can affect the power system. We see some studies from Sweden where they have compared technology neutral case studies against some 100% renewables case studies. We see this dispatch curve from hydropower in the different cases. So the blue one is actual data or hydropower dispatch from 2018, and these case studies are renewable or 100% renewable and low nuclear buildouts. We see that hydropower has to operate much more often at higher power outputs in order to back up the intermittent energy sources, and they also produce less. So there's much higher ramping and utilization of hydropower in these 100% renewable cases. But this is also something we are going to investigate and see if we see something similar effects in the Norwegian hydropower system. And yeah.
Could you take 1 more minute? Is that?
Yeah, sure. I'm soon done. And also nuclear has some flexibility to provide. We see from, sorry for the typo, but we see some from French reactors where they're able to provide 10% for balancing power. And they're also able to have a daily cyclist where they go down to 50%, because they also go a bit further down. And the same is with these SMR, where we can see a case study where they use a new scale SMR together with a wind farm in order to balance the power output. So there are some possibilities for from nuclear to provide some flexibility. But as Jonas mentioned, in Norway, we have a lot of hydropower that could take this role instead if we get more nuclear in to alleviate hydropower. Some other interesting studies we can do it. There are a lot of industrial consumers in Norway that lives where there is a sparsity of grid connections to the areas. So you can either build new grid and a new power plant somewhere to supply, or you could put the SMR close to where the industrial need is, and you don't have to build out the power grid instead. So you get some additional savings by some system cost savings. And also there are some very interesting properties of molten salt reactors able to provide load following capabilities. We talked with the CTO of a Canadian molten salt reactor firm. He said that they could at least provide 10% ramping capabilities, and he was optimistic they could do 10%. And I think hydropower is around 15. So there are some, in a world where a backup capacity is needed, it's a very interesting reactor to do some studies about. Yeah, and also as Jonas mentioned, these other valuable properties that comes with having large machines rotating in the power system. So I can also just mention briefly that we are going to look at some of these fusion technologies. There are some gain some knowledge and understand a little bit of how they can affect the power system and see if there are some challenges. For example, this ITA project, I think that they need around 200 megawatts in order to supply the control system, pumps, valves, everything just in order to have the power system operating. So in order for that to be economically feasible, you would have an enormous amount of electric output. So this will also be some huge power plants. So I think I'll round it up.
Thank you. Great. I turn it over to Goran Durakovic. Please take it away.
Thank you. So before I get going, let me just say that I agree with 90% of what was said in the last 30 minutes. Nuclear power is probably, or pretty surely, the most dense energy source that we have. And also, it is true that per unit of energy produced, nuclear power is the safest in terms of health consequences. There are some other challenges where we disagree, though, and I will cover those in this presentation, where, yeah, me and Stian did a quick analysis on nuclear power in Norway, the Nordics, and Europe. Before I get going to the analysis itself, I want to talk a little bit about the model that we use. So we use a model called EMPIRE, which has been developed at our department for the better part of 10 years. It has also been used in different European Commission studies, and of course gone through rigorous peer reviews several times. So it's a well-established model. I won't go into detail about the model unless you're curious about it and want to ask me later, but there are two main things that I want to emphasize here. One is that EMPIRE optimizes, based on cost, the investments into the European power market. So it builds capacity to meet electricity demand. But not only that, it also optimizes the dispatch, that is the use of these power generators and transmission lines in the European power system. So it does this on an hourly basis, much like the day-ahead market on, well, any power market in the world today. So in that sense, it mirrors the real-life market quite well. Another thing is that EMPIRE features uncertainty, and this uncertainty comes from electricity demand in each hour and how much power renewable generators produce in each hour. Again, in real life, we're not entirely sure in each hour how much electricity we need or how much power we get from our renewable generators, and EMPIRE includes this in the modeling itself. On the right is a figure of EMPIRE where we show all of the nodes where we optimize investments in EMPIRE. So you'll see we have the 5 price zones for Norway, and we have 1 node per country in Europe. We also have the offshore wind parks off the coast in the North Sea, quite well modeled. So let's talk a little bit about nuclear power in EMPIRE. Usually in EMPIRE, we follow political guidelines when it comes to how much we can invest in each technology. So when it comes to, for example, nuclear, historically, we've taken political decisions and set that as a cap. So for example, in Germany, where they've decided to phase out nuclear completely, we've included that in our model. Same goes for, let's say, biomass or biopower, where we can't build infinitely many farms or forests. So that puts an upper limit on how much bio we can use. Same goes for wind, same goes for solar. In this investigation, we've completely relaxed the limits on nuclear power. So every country can build infinite amounts of nuclear power. Another important characteristic is that EMPIRE is a model of real life. So there are some simplifications that we just don't capture in the model. And these are, when it comes to nuclear power, costs. We don't capture costs related to waste handling. We don't capture costs related to risk. And I'm not talking about a risk related to a nuclear catastrophe. I'm talking about risk related to delays in construction and these things. And also, we don't capture political opposition directly. So we have these maximum capacity that we can set, but once we allow for buildup, we don't have any kind of opposition to a buildup of a technology in EMPIRE. So in our investigation, what we did is we first we ran the relaxed nuclear constraints with our base price, and then we reduce the price by 25% and 50%. The price for a base kind of level comes from the European Commission. It's from the EU reference scenario that takes inputs from over 100 industrial stakeholders, and these set the techno-economic parameters for the generators in our model. The 25% reduction, that is the level where the European Commission has put, that's the price that the European Commission foresees if we get the economies of scale effects that a large buildup and small modular reactors will allow. We've heard the price of 3,000 euros per kilowatt earlier today. We've also ran this. This is what the industry is telling us they can maybe reach. And this is the most optimistic cost that we have ran with in our model. But we make no guarantees about these numbers being correct. And if we look at the projections, we see that the cost we have in our base empire is roughly in line with the projections that are out there. The 25% reduction is kind of lands straight in the middle of the most popular area, whereas the 50% reduction is on the lower end tail. However, if we compare this to historical realized costs, we see that even our most expensive estimate is well below the cost we've actually seen in real life. So this is something to keep in mind. Where if we look at the 50% reduction, this will be very optimistic compared to what we've seen in the past. Okay, with that out of the way, let's get into some results. First, focusing on the nuclear, on the European level. And this is for our most expensive cost, 6,000 euros per kilowatt. And what do we see? Well, first of all, we see that if we relax the limits everywhere, nuclear can play a massive role in the European energy decarbonization. And we see that in Europe, nuclear accounts for roughly 7% of the capacity. In Germany, it plays a massive role. And this makes sense. Germany has a massive power demand today, and this will only continue to grow into the future. So Germany has a massive potential to take up nuclear power, political problems notwithstanding. Other countries also have potential to take up nuclear power. I've chosen to include Great Britain, which in this case picks up nuclear power at around 3% in 2050. But as we know, the UK has focused a lot on wind, both onshore and offshore, and that is reflected also in our results. So what happens if we halve the cost? Well, as you can imagine, the capacity explodes. In Europe, the invested capacity grows to around 15%, but in Germany, it grows to almost 60%. It just goes to show that carbon-free dispatchable power is extremely valuable, given correct prices. We see the same in Great Britain, where, again, it just increases by a lot. What then happens if we put limits on Germany? Well, can we take that afterwards? Or do you want to know now? It's 11 megatons in 2050. Or hard cap.
How many it is?
1,100, I believe. So in 2020. Maybe Stian can confirm.
Yeah, it's perfect.
Right. Limiting the investments in Germany. As you can imagine, it goes to zero in Germany because we don't allow it. But we see a larger uptake in Great Britain, mostly because now Great Britain can't import this power anymore from Germany. And Europe stays roughly the same. It goes a little bit down, but not by much. In Germany, what happens is that renewable power grows by a lot, mainly solar. And actually, if we compare the two, if you focus in this area, in the renewable section of Europe, we can see that it grows by a lot. massive effect on the European power grid. So what about the Nordics? Well, for our base assumptions, old reliable Finland still buys a lot of nuclear power, in line basically with what they've been doing for a while now. And it buys a lot, mainly because the power demand also increases a lot, as we've seen so far. Surprisingly, looking at Sweden, nuclear power gets completely phased out. Slowly but surely, existing capacity just dies away in favor of wind and biopower that we see here. Denmark, that hasn't really had any history with nuclear power, doesn't invest in this case either, focusing a lot on wind power, as Denmark has been known for a while now. No surprises with Norway, no nuclear power. Instead, we focus on hydropower in yellow and wind in blue and purple. Reducing the price by half doesn't change the picture much. Even in our most optimistic scenario, the picture looks practically identical. The capacity in Finland grows by a little bit. Sweden looks practically identical, as does Norway. Denmark, in this case, buys 500 megawatts of nuclear power. You can't really see it. It's a tiny sliver on the top. But yeah, even here, there's no nuclear power in Norway. So what happens if we reduce the investments in Germany? Well, something interesting happens here, actually. We see that now we get quite a significant uptake of nuclear power in Sweden, and especially in Denmark. This makes sense. Suddenly, Germany goes from having over 50% of its power grid from nuclear dispatchable power to mainly relying on solar. And it needs some dispatchable power from somewhere. So instead of buying biopower, which is carbon-free and dispatchable, it instead imports from Denmark and Sweden. Both of these are well connected to Germany, which allow Germany to utilize this power, even though it doesn't invest itself. So what about Norway? In our most constricting scenario, in our most nuclear favorable case for Norway, Norway still does not invest in nuclear power. Wind and hydropower is sufficient, where wind gives a lot of cheap electricity to the grid, and when there's too much wind, hydropower can pick it up and release when there's too little.
2 more minutes.
2 more minutes, gotcha. And we've been talking a little bit about small modular reactors. So far, we've been focusing a lot on kind of utility scale, large projects. But small modular reactors are also interesting, mainly because then you can put them in more decentralized areas and use them for more exciting capabilities. The problem with nuclear reactors is that they don't exist, at least in the West. There are projects in Europe and in the Americas to build nuclear power SMRs, but they, as far as I know, are not going to be delivered before 2029 or 2030, the earliest. And as such, we don't really know much about the costs from these. But in this year, we gained some insights. So NuScale is one of the projects that was mentioned earlier, and they, in January, did a mandatory revision of their cost estimates. So from 2016, they said that they could deliver power at $55 per megawatt hour. And then in 2021, they scaled the project down a little bit, fewer reactors, so the price went up a little bit because the smaller effects from economies of scale, but still very reasonable at $58 per megawatt. In January, like I said, they updated their costs. Oops. Suddenly, we're reaching $120 per megawatt hour, and they get a $30 per megawatt hour subsidy. Now, this graph is a little inaccurate. There are 2 subsidies. It's not just the Inflation Reduction Act. The Department of Energy is sponsoring them also with $1.5 billion of American dollars. This investment capacity lands at $20,000 per kilowatt, blowing up the scale that we saw earlier by far. for transparency's sake, they're saying that this is because of inflationary pressures. The cost of steel, the cost of wires has gone up, which causes this. But if we look at the cost for wind power in the same time frame, we do not see this insane explosion in prices. So you'll have to forgive me for being a little hesitant on nuclear power. So to summarize, in Europe, we see a massive potential for nuclear power, much higher than it is today, where we can go to maybe 7%, politically allowing, of course. And Germany is a very nice area to build in, but unfortunately, very difficult, as we know today. In the Nordics, only Finland really has the conditions suitable for nuclear power. In Denmark and Sweden, in the cases we've studied, nuclear power is usually outcompeted by renewable generation, except for when Germany phases out their nuclear capacity, allowing Denmark and Sweden to build them themselves and export it to Germany. In Norway, we don't see any cases where nuclear power is built. And what we see is that hydropower and wind is more than sufficient to meet the Norwegian demand, and still Norway is a net exporter in 2050. So our assessment based on this is that we don't really see, as things stand today, that nuclear power will play any important role in the Norwegian power system today, in 10 years, or the future. But that does not mean that we should discount nuclear power entirely. We should still keep our eyes out and see what happens with these developments. We should just not be early adopters about new, unproven technologies. If they are as cheap and as good or better than what the nuclear power companies promise, then we can consider picking it up in Norway. But until that time, we should just wait and see what these projects really cost, and maybe moving into 2040, there's some hope for nuclear power. And with that, thank you for your attention.
Great, thank you very much. I will invite Jonas to join here as well for the Q&A. And Martin will have to invite you again, but also feel free to jump in if necessary, but just to keep it simple. Yeah?
You can turn on.
Do people online still hear us? I guess that it should be okay. It should be okay. Well, great. So because I organized this, I get to ask the first question. And then we'll move on to you, the audience. So I heard a lot of agreement here, and you know, in particular about the big role that nuclear could play in certain countries. Maybe the one sort of divergence is maybe with the policy recommendations for Norway. You know, kind of focusing in on that for now, I would like each one of you to give the best reason why your conclusion might be incorrect. So what is the best counter argument?
Again?
Sorry, yes, feel free to begin.
Okay. Like when it comes to onshore wind, I think we are in agreement on that, but I think that this scenario that you have is not realistic in my opinion, that we will not get this build out of onshore wind in Norway. I don't think that's possible. So therefore I think that when you had run the scenario then, I don't think it's a wise decision of Norway. Why should Norway build the most expensive offshore wind power in Europe? I don't think that is a good investment. Of course, we can build some of it, but we should have. It can fail. It has failed a lot of times, like in Japan and so forth. So it would be more wise, I think, to maybe have some extremely expensive offshore wind and some nuclear. I think would be a wiser decision. And if you look at the DNV prospect for 2035, their conservative estimate is 97 øre per kilowatt hour, and for the optimistic is 60 øre per kilowatt hour.
So just to clarify, the best counter argument to your conclusion is that offshore wind could also be valuable.
So
is that right?
if nuclear power has the same LSOE as nuclear power is by far more cheap than offshore wind. So now offshore nuclear, according to NVE, is half of offshore wind in Norway. So we are a long way above, and even with the most optimistic estimates, the most expensive offshore wind in Europe will be about the same price as nuclear is in Norway today. But I don't believe, I think the conservative estimate of 97 øre per kilowatt hour is more reasonable, because bottom fixed offshore wind is a very, very mature technology. You have had for land-based wind and for bottom fixed offshore wind, you have the 15-fold increase in turbine size. There's a lot of learning. The learning is finished, so I don't see the prospects of cutting costs. And therefore, my case is like, if you you put a more realistic scenario on the onshore wind, you put a more realistic scenario on the offshore wind, and nuclear will play a major role in Norway. And also, if you, instead of focusing on optimizing the European energy system, you focus more on optimizing the Nordic and the Norwegian energy system. That is what we will do in our project, that we will focus more on this system, and we also think there's not so much. It's not easy to build more cables to Europe, so we believe that is also another.
Yeah, thank you. Yeah, just to clarify, the question was why you might be wrong, not why the other side is wrong.
Yeah, but I think.
But I think we'll move on. We'll move on. I think Goran probably wants to follow up, but I'd also ask Goran to say why his conclusion might be incorrect, since that was the original question. But I will let you also follow up briefly, please, and then because we want to get to questions from the audience as well.
Of course. So just to reply, I didn't show it in the results here, but we did run a case where we didn't allow for wind build-out in Norway. So we capped onshore wind investments at 1.7 gigawatts. That's less than a third of what we have today installed. Even then, nuclear wasn't built out in Norway. Just to get out.
Based on your assumptions.
Based on my assumptions.
Yes.
Now, to why my conclusion might be wrong. My conclusion focuses a lot on the power system. We optimize based on available transmission between price zones, right? From, let's say, Oslo to Kristiansand to Denmark, etc. There are some details there that we don't capture. We also don't consider other energy forms. Heat was mentioned earlier, for example. That is not explicitly captured in our model. Industrial heat, I should say. We do have domestic heat. There could be some playroom for nuclear here, maybe. And that's why I welcome the NERES project that was introduced earlier. I'm very curious, once you actually get into the details of individual case studies, what is the feasibility of nuclear? Is it economical to build? And if not, what would it take? So those are kind of some weaknesses in our assumptions. But on the power system side, I think we tackle things quite well.
Okay, thanks for that answer and the clarification as well that we got. So we turn to questions from the audience. There's already questions online, but I will start with the room, and Ruud goes first. Thank you.
Thank you, gentlemen. I really appreciate both your presentations, and I think also the tone thus far has been very pleasant. I think it must be nice to keep it that way. I want to challenge Jonas and Martin a little bit on flexibility from nuclear. The main cost component from nuclear is investment costs, and there may be perspective that these will lower over time. There's a good chance, but you The moment you start using nuclear for flexibility, that means you're going to have fewer operational hours, lower capacity usage. And that will immediately push the capital cost part of the LCOE up. So the more you're going to use nuclear for flexibility, the higher your LCOE will be. And that can become quite drastic if in the future there will be significant periods where there will be zero energy prices and your nuclear would be running because you don't want to turn it off. Is producing, is burning uranium, is losing money. So how do you see that?
Well, as we briefly mentioned in the slide, there are some revenue streams that are not included by only selling energy. So you have these services, also compared to wind and solar, you have huge mass rotating in the system. So you have inertia, you have short circuit power, and these services, if we only built solar and wind, you will have to pay for these services, build up flywheels, or have some SVCs, I'm not sure the name, to compensate. So then you're not only, and these services, the assumption is that these will be in more demand in the future. So that the part of the revenue stream coming from ancillary services could increase enough to compensate for the loss of, or for providing this flexibility. Because of course, if you provide this load following capability from the light water reactor, you are basically reducing your efficiency, or you're losing some energy that could have been sold to the energy. So it doesn't help you to cover the capital costs.
Will we need that in Norway ever? Because we have all this flexible water.
No, that's what we mentioned. Like we have that with hydropower. So, but we also have, Jonas showed this power
adequacy crisis.
Yeah, thank you.
The what crisis?
Power adequacy crisis.
Yes.
But this is projected potentially for 2030, right? And what is the earliest date, if you would go for all your optimistic assumptions, what would be the earliest date that we would have nuclear power in Norway, if it would be allowed?
I'm not going to provide a good estimate, but if you see the Emirates, they decided in 2008, 2012, they started building. And I think 2017, 18, they had the first unit up and going. These were large conventional reactors.
So the majority of nuclear power plants in the world is built in lower time than 7.5 years. So what we hear in the media is just first of a kind reactors. That will, like for any energy solution, first of a kind will be expensive and it will take much more time. It's not limited to nuclear.
And 7.5 years, you would also need this, all the regulatory and so 10, 15 years.
But you should maybe mention the study of MIT about how nuclear power can actually increase the value of renewables.
Yeah, continue.
Yeah, but
Let's get to a question from the audience, but if we have time, we should come back to that. Because there's an audience question that actually relates to the discussion here.
Yeah, sure.
Is that all right? Yeah, thanks. So the question is, SMR is expensive, but at the same time, it might be cheap in the future, and shouldn't richest countries take the sort of burden to adopt the technology early on and maybe help with learning, and that gets to your point, right?
Yeah.
Or on the other hand, should Norway wait until it's cheap to invest? So if there are reflections from anyone,
I can answer from Jonas. Okay. You see, for example, Seaborg in Denmark. They are not building for domestic use. They are building for the Southeast Asian countries, where the only opportunity to have a stable, reliable energy source is coal. So they want to fill that market and provide these power barges where you can haul them to where location you want to build. So, and then they are not doing this for themselves. They are doing this because we everybody in the world has to reduce their CO2 emissions, so they try to help out the poorer countries with their technology.
I see. It's a question of building an export industry for you,
that as well,
rather than like using it domestically, or at least that was your answer. But okay, Goran, what do you think?
Yeah, so when it comes to who should pay for the development of these, I think it's an interesting question about how this cost burden should be shared in mainly industrialized countries. I believe that industrialized countries have the opportunity and the muscles to develop these technologies. The question is, Norway, with no experience in nuclear power development, no experience really of any note when it comes to nuclear power at all.
That is wrong.
Yeah, except for the Fed that shut down a couple of years ago. Should we develop this instead of Great Britain, France, the US, Korea? There are plenty of countries with much more experience than us that can actually make an impact here. We would just be sinking money into a hole.
I see, okay. So disagreement about the sort of national capability.
The same argument goes for floating offshore wind. We have no experience with that either. So the thing is, we have two technologies that Norway does not have any major previous experiences on. And the challenges of building out a fleet that provide energy and power from these sources takes a long time. So speaking of risk management and trying to see the short time span we have to build out more climate-friendly electricity, wouldn't it be wise to have two streams to bet on? If one of them fails, you at least have another one. You don't have to wait another 10 years.
I feel like Japan lost 10 years when they shut down the floating wind. Like they lost 10 years by not being more strategic.
So just to follow up on that, we as an oil and gas country for 60 years soon to be, have a lot of experience with marine installations. And we already have quite a lot of experience with offshore wind project handling in our oil and gas companies, or I should say Equinor here to be quite specific. We have a large value chain dedicated to the offshore oil and gas industry that can be leveraged for offshore wind installations. And that's what we're doing.
But the same oil and gas industry can do similar services for the nuclear industry. It's process engineering. It's pipes, it's fluid flowing.
I reject that wholeheartedly.
I guess we will not agree on that today, but I see a burning question from Ruud. I know Hussein is next, but I think Ruud wants to follow up directly. So
some things here, right? So you say Norway doesn't have experience in floating wind. To counter Goran's argument, but that France, Great Britain, US have more experience than us. It's not the same argument, right? If nobody has experience, you can be the first one to gain experience and get leverage. If others have a lot more experience, you have a gap that you need to overcome. And then in the relative competitiveness, and that is very often in these economics thing, it's not about absolute, it's about relative competitiveness. Norway is behind. Japan is a country that imports 97% of their energy needs. Norway is a country that exports 4 times, 5 times as much energy as is used domestically. It's a completely different starting point from how they strategically should manage their energy system over the next 30 years. So be careful which systems, which starting points you compare before picking them to use them in a debate and try to counter an argument.
No, but then it's saying like the Emirates. One of the reasons they are building this nuclear fleet is so they don't have to burn coal and gas locally and then export more.
But that's a short-term strategy, right? Because Norway and Europe have committed to decarbonization. And there's another thing with the United Emirates. It's a dictatorship. Yeah. If there's 5 people there and the top who agree that something is good, then they can just choose. And in a democracy, you have all these checks and balances that will be in place and that are going to take several years.
You have also another perspective is electricity prices, because if Norway don't get nuclear, they will not have as low electricity prices as they could. And And that is very important for Norway. Norway has historically had much lower electricity prices than other countries. If we have the same electricity prices as Germany, Norway will not have any benefits in electrification, I would say, because we have other disadvantages like a cold climate, and we have it costs more to do things. So we have to have this factor lower electricity. And that's the exact same thing that the Arab Emirates did. It's very expensive electricity when you burn gas and coals to step in. It's much better to have such base load to push the electricity prices down the whole year. If we don't go nuclear in Norway, we will have much more price spikes. The average price will be higher, and it will not be wise to not consider it, to consider that having low electricity prices can be a competitive advantage for Norway.
Just to clarify, is that something you're modeling in your upcoming work? Because you're talking about electricity prices.
I just discussed the concept here, the concept of having a low marginal price source to push down electricity prices the whole year, not just 30% of the year.
Okay, conceptually, got it, yeah.
The challenge to that is I've never seen this in any publication whatsoever. Hydropower.
It's a hypothesis.
Right,
yeah.
But you're presenting as fact, and you need to be very clear about what exactly you're talking about. Nuclear power maybe in the future, given the costs go down, could be competitive with onshore wind and hydropower. As things stand today, based on publications by the International Energy Agency, Norwegian hydropower and onshore wind is half the cost of nuclear power in using Western standards. And I don't see that going down, even with the new scale.
LCOE, right?
Yes.
Well,
that is not electricity prices. LCOE, like you could have really low LCOE, you could have disastrous electricity prices still.
I know. But our model takes into account imbalances caused by renewable power. It takes into account grid developments that you have to build to balance out and disperse the renewable power. And still, even with 3,000 euros per kilowatt, we do not see nuclear power in Norway.
Yeah, so we'll have higher average electricity prices.
Not true.
Yeah.
So this is a great discussion. We're already over time, and everybody's still here, which and a lot of people online, which tells me that it's very interesting to all of you. So it's great. I know that Hussein had a question, and I wanted to get to that. If you have to leave, that's fine. But I want to give the opportunity to Hussein as well.
Well, thank you very much to give the opportunity. It's a very short question, and thank you very much. It was a very nice discussion. It was discussed that, okay, if we want to have a nuclear power empowering the entire Norway, we need a half a country of beacon. But did you think about also transmission expansion? We generate power is in a very concentrated area, but we need also to transfer it. We need also to send it all over the country. Then we need to expand the transmission and get a lot of also land use in a way, in this case, which is an argument to have nuclear power in the country. And I like also your idea, Goran, to look at also transmission expansion, because we talk about also like onshore wind, offshore wind, and offshore wind also we need to expand our transmission system quite significantly with respect to that. And that is part of the cost, but it's part of this equation. Maybe when we talk about also nuclear power plant, SMR, that is very promising, this technology on IEA reports. They talk about that, but the technology is not ready yet. That's a problem of nuclear power plant for the time.
So I guess there was a question and a comment about SMR and the question about transmission. Did you want to follow up on that? Did you have?
Yeah, I agree with the comment about transmission. I mean, transmission has also seen widespread political opposition, right? Or public opposition, I should say. But if we're going to really start lobbying for either transmission or nuclear power, I would say transmission 100% of the time. Transmission allows us to build much more cheap renewables, and it allows it to be transmitted to the point where it's needed at the right time. But given that we really can't, and we have limits on this too, of course, in our model, we need to look to domestic production instead. And then, that's where our results come.
So what we are trying to do today without nuclear playing a role is to have a over-dimensioned power system with very, very low utilization. And we haven't tried that before. It's an experiment that we're running. It has been a disastrous experiment in Germany. You can see, like last year, France had five times less emissions. Then France had 5 times less emissions than Germany. Still, it was the worst year of France ever. 40 years of super high capacity factor. Their whole fleet needed to have maintenance. Even in the worst year, you have disastrous amounts of emissions in Germany trying this experiment out. So I would say that we should be a little bit conservative. Making a power system like without nuclear in Norway, we need 3 to 4 times more electric capacity on the electricity grid. It's going to be really, really expensive. It's going to be really takes a lot of time. The system cost is going to explode. The need for ancillary services is going to explode.
Please understand also my comment. I have also the same comment to nuclear power.
Yeah.
You generate also power in one place, but you need also to export that. Then you need to expand also the transmission line quite significantly, to be honest.
The nuclear will free up capacity of the grid and also of the hydropower power to make it easier to build out solar and wind. So what you see with solar and wind is that in the beginning, you lean on the infrastructure, you get a certain percentage, it's cheap, and then you get to a certain level, the transition gets more and more difficult, you get lower and lower value of the new renewables because of the value factor, like the price cannibalization. That is the benefit of nuclear. It doesn't have this value drop. That's the reason we need to have a robust energy mix. We can't be ideological. The experiment in Germany has been a disaster. We need to change our mind.
So it sounded like there was another hypothesis there about transmission and the role that nuclear can play in alleviating transmission limits or requiring new transmission. So maybe as a researcher, I like that we're talking about hypotheses. It gives us more to do and more research to do in the future. I see that there's a burning question here. Please, PJ, go ahead. Yes.
Jonas, was that a hypothesis you are planning on investigating in your project, that the nuclear will free up the transmission capacity?
Yes.
Okay. We are looking for the results.
Yeah, but I've also talked about the airport, that you could decarbonize the airport without transmission, without hydropower, without transmission, synthetic fuels, hydrogen production, just as it's done today.
I wish you the best. Thank you. And thank you very much.
Great.
A quick follow-up.
Okay, a quick follow-up. All right.
So just 2 things. It's important to clarify here. One about the transmission thing. It definitely sounds like a hypothesis, this about over-dimensioning transmission lines. If we relax our limits on transmission lines, they are used extensively. They are not used just 1 or 2 hours per year. They are used all the time. Second of all, you mentioned the emissions from the German power sector last year. So, as I'm sure a lot of people in the audience know, last year was quite exceptional in the European power energy markets, right? Natural gas, which Germany has relied on for quite a long time now, was basically cut on the day. And that forced Germany to switch to coal power. I agree if they hadn't had dismantled their nuclear capacity, their reliance on coal would be smaller. But let's not kid ourselves and say that last year was a normal year for either France or Germany. We also know that France, with its nuclear fleet, had tremendous problems last summer with not sufficient cooling capacity, and the French nuclear fleet has been basically down for maintenance for, not all of it of course, but a significant part has been down for
after 40 years, yeah.
Yes, but still, that caused that Germany required. Speaking of anecdotes, Germany has to power up their generation in order to power France, causing German coal power to emit a lot of CO2 in Germany on France's behalf.
Right. So I think we're seeing nicely how in research we try to explain what happens in the real world, and our models can only try to do that. And we're asking hypotheses. I think Ruud has the last word, and then we.
Okay. So I think you started with saying we agree on 90%, right? And there's a couple of things where we don't agree. And I really have respect for both of you that with your opinion, yeah, which is really not inside the mainstream, you're going out there and you're trying to get the debate and or to have the debate. And I think at least I'm very sensitive about this topic. I think several others are too. And it tends to be heated because some of the things are very far apart. And I think if we continue these exchanges, yeah, and we industrial economists can help you to get the economics a bit better, and we can learn from you how the nuclear technology benefits a broader system, we can actually have synergy here. And continuing disagreeing, but still have synergy in getting our concepts better in place in an economic context. So thank you very much.
I completely agree. We need to have some disagreements in order to have innovation. We need to have thesis and antithesis. If you don't only have dogmatism in science, you will not get a step further. You need to have some skepticism. Of course, we should be a dogmatic about things that are established, but we need to allow some skepticism. Therefore, I think it's very, very fruitful to have some disagreements to make room for new ideas and for innovation. And the final advice I would give to all of you is to download the app Electricity Map, where you can kind of track the greenwashing real time.
So I want to thank all of the speakers and the audience as well for a great discussion.